All right, perfect. So now it's 11 o'clock and I actually get started with the webinar itself. So first off, I'd like to thank everyone that is here today for taking time out of your day to participate in today's design tips webinar centered around designing a gantry robot in minutes. My name is Jeremy. I'm the education lead here at Vention, and my role is essentially to educate users on how to use our design platform, which is the machine builder, what we'll be seeing a little bit more of today, as well as the simulation and programming software, which is Machine Logic, that also does live within the machine builder location. With that, I'll actually jump right into the agenda to see what we'll be covering and how this webinar will progress. So just a quick note about this webinar will be centered around a mock project that I would like to design / deploy on my theoretical shop floor. And to go about this, what we'll be doing is evaluating my theoretical project specifications and then selecting actuators based on these specifications. From there, we're going to do a little dive into Vention's resource library to make sure that the hardware that we selected is valid for our application. So again, just validating the hardware. And finally, getting into the main portion of this webinar is actually designing the gantry robot itself. This includes the actuators, the 3-axis system that we'll be working towards, as well as the substructure. So throughout the webinar, there are a few different ways that you can interact. The first being the Q&A section in the bottom of the Zoom platform. This allows you to ask questions to myself throughout the webinar. And I do have my colleague on the line here, Caroline, that will be monitoring this. So if she does have answers readily available, she will answer them in the Q&A section. If not, if they are relevant, I will try to voice them out and answer them live on the webinar itself. If I don't get to them by the end, we will try to answer them at the end or answer them in an email that will be sent out afterwards. Also, if you'd like to chat with other participants, there is a chat section if you'd like to do that. And finally, there will be an open mic portion where you can ask questions both to myself and other participants at the end. One thing to note is this webinar is being recorded and will be sent out to all registrants and will be posted on both the Vention website and the YouTube page if you'd like to refer it at a later date. So with that, we can actually jump directly into the webinar itself. And starting off, the first one is going through my mock design that I'd like to work towards. So defining the project requirements. So for this project that we'll be looking at today is going to be a 3-axis glue deposition machine. So it's going to be an X, a Y, and a Z, not a theta. So with this, the largest SKU that I'm looking to say deposit glue on, the largest panel, is a panel of 1200 by 600 millimeters. So this has a 1200 by 600 millimeter footprint. And this will later drive the selection of our actuated travel length. Other than that, we do have a few different requirements. First being that it is a high precision machine that we're looking to do for these small features, looking for approximately smaller than 0.1 millimeters. In terms of load, we're going to assume that we have a negligible load, really just the actuators themselves and the glue deposition end of arm tooling. For the environment that we plan on deploying this in, we're going to say that it is a clean environment. And finally, the required speed that we're looking to have is approximately 300 millimeters per second. If you're looking to say design your own gantry robot or are looking to deploy, these are some of the basic requirements that you really should be thinking of before going into the design process. So with this information in mind, we're going to go to our website over here and look at what some of the resources that we have that are useful for actually selecting the actuators. So going over to the resource tab over here, we'll navigate to the resource center. Over here, I'm going to type in selecting and confirm. So what this will bring us to is a document called Selecting Your Linear Actuator. What it does is it gives a brief overview of all the linear actuators that we have on our platform. This includes our enclosed timing belts, enclosed ball screw, lead screw, belt rack, as well as the rack and pinion actuator. It gives a brief overview of what they are used for, their available lengths, configurations, etc., as well as some of their torque curves. If you scroll down to the bottom of this page, there is a flowchart that does help you select what type of actuator you should be looking to use for your application. Just to give people a little bit of a better view, I'm going to be bringing up another version of it over here. So again, if you do have any questions, feel free to either raise the hand in the Zoom platform or ask a question in the Q&A, and we will try to answer that as soon as possible. So continuing on over here. So we are looking to do a 3-axis glue deposition. So we have 3 different axes that we're looking to select actuators for. First thing that we have to choose is the travel. So like earlier, we're looking for a SKU that is 1200 by 600 millimeters in footprint. So if we're looking for something that it can go up to 3,200 or larger than 3,200 millimeters, we can go with availability all on the right. But looking at our actuator, normally you do want one that's a little bit larger than your travel, but not, say, excessively too large. So this, going with something that's a little bit smaller than 2080 millimeters will most likely suffice. After that, we're going to go over the load. Like earlier, the load is something negligible, really just has to support the weight of its own structure and other actuators on it. So we can go down to the 350 or the less than 350 newtons. Say you are doing something that does have, say, some force feedback, say milling or drilling, it might be recommended to go something a little bit heavier duty. From there, we can go down to the speed. Again, like I mentioned, looking for approximately 300 millimeters per second. So going to go down on the left side as well, going for less than 900 millimeters per second for the selection. And then from there, repeatability. Like I said, I was looking for less than 0.1 millimeters. So our actuators usually have one of two different repeatability options. First being less than or approximately 0.25 millimeters, the other one being 0.025. Since I did 0.1, this one will not function for what I'm looking for. So I'll go for the 0.025. Then finally, for the environment. In mine, I did select clean. So it gives me options to select either the timing belt, enclosed timing belt, enclosed ball screw, pardon me, or the belt rack. Say I would be going for a dirty environment, that does leave out the timing belt and the belt rack, as they are not enclosed actuators. In my case, I will most likely select the enclosed timing belts and the enclosed ball screw just for future proofing. Say I do want to repurpose this machine, they do have higher load ratings and can be used in different environments afterwards. So that, since I've selected the type of actuators, or I've assumed that I'm going to be selecting these ones, I can actually go back to the Vention website and see if these are actually applicable. So what I'll do is go to the parts library, down to linear motion, and this is where we'll find all of the different linear actuators we have. Say I want to take a closer look at the enclosed ball screw. I can click on it over here, scroll down to the documentation, and select enclosed ball screw actuator. So all of our actuators that we do have on our website do have their own technical documentation, which give a brief overview of their internal components, their hardware, their setup, as well as their most likely used applications. Some of the most useful information for us that we would be looking at, if we scroll down to the base over here, is the technical specifications. So that's repeatability, accuracy, whether it has high backdrive resistance, which is something that you should be looking for if you want to have it, say, mounted as a Xaxis, their available lengths, and also the load capacity, depending on the X, Y, or Z axes. And finally, again, for the loads, if you do want to calculate to see if the actuator is able to withstand the load that you're trying to drive, we do have our output force versus speed curves using the three different motors that we have. So we have a small, medium, and large NEMA 34 stepper servo motor. So from there, I'm going to jump ahead and assume that we have validated all of our three actuators. So this is going to be a standard enclosed timing belt, a heavy-duty enclosed timing belt, and an enclosed ball screw. So assuming that we validated that, we actually get right into the designing portion. If there are no questions about the resource library, I can get started right with the designing. And looks like we're good. So this environment over here, for those that are a bit newer to Vention's platform, this is the machine builder window that you see over here. So this is really the design platform where you can build or assemble your structures. The one that we'll be focusing on is the gantry robot. I would like to note that I will be, say, using a few shortcuts that have been covered in previous webinars. So if you do see something that you'd like to have me elaborate on a little bit more, feel free to raise your hand. So I'm going to start off with the linear motion for the Y-axis. So like I said earlier, I'm going to be selecting the enclosed timing belt. But first, I want to select what is the length required. So looking, we do have the largest length of 1200 millimeters for the footprint of our piece that we're looking to work on. So in the drop-down menu, you notice that we have a 585 millimeter length, 855, 1530, 2295, and finally a 3300. In this case, the 1530 can possibly function for it, but if you do take into account that the structure and the end of arm tool will make you lose a little bit of travel, it's better to opt for something a little bit longer or do the full calculations to validate. In our case, since I do know we will be needing the slightly longer one, I'll opt for the 2295 millimeter actuator. You'll see the design software, for those that are new, it's really a click and click interface. So once I click the part on the left, click it to confirm its location in my design space to confirm its location. On the left, we have a configuration assistant here that you can toggle on and off that does pop up when you add in a piece of automated machinery. What it does is make sure that you do have all the automated components to make sure it would function if you were to purchase this and deploy it in real life. This includes, say, motors, guidance systems, the controllers, as well as the e-stop. In my case, I will click autocomplete to automatically add all of the parts to the actuator, add the machine motion controller, and then finally the e-stop off to the side just to make sure that it functions. For the rest, if you do like, say, trying to design by yourself and don't actually need all of the automation components, you can toggle this off in the menu, go to settings, the smart design, and clicking off configuration assistant. So from here, this is the start of our Y-axis. So if you did note earlier, again, the footprint that we're looking to do is 1200 by 600. So doing a top view over here, that means we're going to have, say, 1200 parallel to this axis and 600 perpendicular. So that means I do have to have a space or a distance between either the two guidance systems, or the driven and the non-driven side, of 600 or more. One thing to consider is if you do have a spacing of more than 500 millimeters, it's recommended to drive both sides of your gantry system, because if you only have one driven side, you do have the likelihood of causing a pinch point that can damage your actuator or your guidance system on the opposite side. So that in mind, I'm going to actually copy this actuator since it does have all of the required hardware that I already have by pressing Control-C and then pasting with Control-V. With this, I'll just align them together just for visual representation. So from there, I have the basis of our y-axis. I'm going to bring in the x-axis, which is the one that will rest across. So for this one, since it's going to be supporting a cantilevered Z, I'm going to opt for the slightly heavier duty enclosed timing belt over here. Again, this one I've pre-selected the length, or I know what length I'm going to be using. But again, when designing, you can always change it out for something a little bit shorter, a little bit longer, if your application or your requirements change in the future. So I'll drop in the 1530 timing belt and reorient it in the orientation that I would like to actually see it in during use. So again, just rotate over here. Some of these tools that I just used is I can right click and then select the ability to move and rotate, or left click and using the navigation compass to the same end over here. Now that I have it in the right orientation, I need a way to actually attach it to my structure. So this, we have actually designed specific mounting plates for mounting actuators to one another, and these can be found under the gantry plate section in the linear motion category. So what I'll do is first select the actuator mounting plate and drop it into my design. But zooming over here, really what it is, it's a plate with the most amount of mounting holes possible in terms of what we have in our parts library. So all of these over here are through holes that are counterbore on one side, and all the ones that have the chamfered edge are tapped holes. In this case, I'm going to first select this and attach it to my structure to begin with. So again, the shortcut that I used there was a point-to-point connection, or you do have the ability to drag and drop, but since we have so many connection options, it's a little bit faster and smoother to use the point-to-point connection tool. From there, actually, let's get this guy out of the way. I want to attach, have a method to attach the actuator horizontally. So with that, we have our gusset plate meant for 90-degree actuator mounting. So again, I'll drop it in place and do a brief overview. So on the front over here and on the underside, these are all tapped holes, again, to offer the most amount of mounting possibility, the greatest amount of mounting possibilities. Again, using point-to-point connection, attach it to the design over here, to the structure, and then using my arrow keys to reorient. So again, what I'm showcasing is a little bit of the power of Machine Builder and also some of the hardware that is recommended to use when you're designing a gantry robot yourself. If you are, say, interested in learning how, there is a tutorial on designing gantry robots that does follow some very similar steps to what I'm showcasing right now. So for this one, we're going to have 3 of these mounted over here. And again, another shortcut that I'm using, you'll notice that I'll click on a part and then the part will appear at the end of my cursor. What this is me pressing the I or the insert key and allows me to reinsert the last clicked or the last inserted part in my design. Finally, I'll click on the gantry plate and insert it into design and attach it to my structure. So with this, I'm going to select the corner over here and attach it. So that we've now completed a location to mount our horizontal or our x-axis on. However, we only have it on one of the two. So again, I'll use the copy paste feature by selecting the hardware that I would like to copy, pressing Control-C and Control-V to drop it down into space. Again, point-to-point connection, just for the speed of designing and attaching it there. So now that we have our y-axis more or less complete, we need to attach the structures together. So attach the x-axis. So this, again, one of the most used tools is either the insert feature or the point-to-point if you are doing more complex machines like this. So this, selected the wrong point over there. Let's go back over here, select the point on the bottom, attach it here, and then rotate using the arrow keys. Again, doing the same. Oh, for this one, I must have, oh, no, we're good. Let's unlock this one, drag it out of the way, and attach it to my structure. So that, if we look closely over here, you can directly mount your actuator to the actuator mounting plate using the counterboard through holes in the back. However, for the easiest way to actually assemble this and mount it in real life, we do have these specific mounting plates or these clamping connectors over here. Essentially, the way they work is as you tighten them down, it will clamp onto the actuator itself, holding in place. It is recommended to have at least 2 per side. However, if you do have the ability to have 4, that is the better of the 2 options. So again, I have 2 on that side, doing the same over here, cycling through the options with my left and right arrow keys. And 2 on this side as well. So that we've essentially finished with our X and Y axes. So these are fully mechanically connected. And if you say were to purchase this design or check out yourself, this would function and would function properly as a XY gantry. However, we are looking to add a Z axis. And like I said earlier, we're going to be using our enclosed timing belt, or pardon me, enclosed ball screw. This one, I'll go down here and select the 585 millimeter enclosed ball screw. This one does not need a mounting interface because on the gantry plates themselves, they do have some tap and through holes that allow for direct mounting. So in this case, I can attach it directly. Oh, selected the point over there. And this guy here. And if I zoom in a little bit, you'll notice over here, we have the through hole, and on the back, this would thread into the threaded hole on the horizontal axis. So that finishes some of the hardware portion of this. Now for automation equipment, if you do have a Z axis, one thing that is highly recommended to add is a power off brake. So what this is, it can be found in controls and motors, is the power off brake over here. What this is meant for is, say in an e-stop or a power situation, it prevents the Z axis from dropping down and impacting any of the hardware underneath the Z axis itself. So from there, that actually finishes the largest portion of designing the gantry robot, and we'll move on to the substructure. If there are any other questions, I'd say feel free to ask them now. If not, I'm going to close off this design and open one where you do have a partially finished substructure. So I'll leave this one over here and open up the second one. So again, one thing to note is the software that I'm using is actually entirely cloud-based. So nothing here is actually housed on my computer. All of this is housed on dedicated servers housed by Vention. So you can access your designs anywhere as long as you do have an internet connection. Again, one of the great things is you can actually share these designs with other collaborators. Say you are working on one by yourself, you started off and realize you'd like to share it with one of your colleagues, you can actually add them as a collaborator. And at that point, they can both edit, view, and modify the design themselves as well. So this, I've jumped ahead to a base frame that is fully assembled, but I will be going over some of the things that should be taken into consideration when designing a frame for a gantry robot. Before that, I'll just zoom in a little bit over here to see the final additions that we've had. So we've added a glue dispensing tool. So over here, this is a wire tank dispenser that can be used for either cobots or mounting directly to the Vention extrusion if you have the appropriate mounting hardware. So this essentially transforms our gantry robot into a glue deposition machine. Again, these can be replaced for either routers or other end-of-arm tools that can be found in the end-of-arm tool section. From here, looking at the frame, I'll highlight some of the key features that really should be thought of when designing it. The first is, if you are again using a designing gantry robot, is to use the largest 90 by 90 millimeter profile for the skeleton or the major portion of the frame. Looking over here, we have a 90 by 90 millimeter extrusion. The reason being is it's our most rigid extrusion for designing. After this is, say you have created your base frame, so you have the top, the base over here, as well as the vertical extrusions, is to mount the ones that will be supporting most of the load in compression if possible. So zooming over here, the 2 extrusions that will be mounting the gantry robot on top of are these 2 over here. And you'll notice that they're resting on top of the vertical extrusion, as opposed to, say, in friction, looking down over here, as one that is resting in between. Again, this is just the best way to support the load. Other things to consider is to make sure that you do square off your structure. So although we do have a center support that will act as the frame that, say, we have our workspace on, always recommended to have a second subframe, again, designed out of the 90 by 90 millimeter extrusion to make sure that it does not deflect or move during operation. After you say built out the skeleton, the next would be the plates and gussets. So if you zoom in, or if I zoom in on the corner over here, notice that we both have external plates and then internal gussets. Really what this does is to make sure that your corners are as strong as possible and will not move during operation. Again, anything is really to prevent either deflection or unwanted motion while the machine is functioning. Finally, from there, if I hide the panel on the side here, would be to add angle bracing where the machine would experience some of the most deflection or say jarring stops. So again, we have some angle bracing over here using some of our inline 45 by 45 millimeter connectors. These can be found again in the structural and framing portion on the left side over here. Reason why I'm just kind of highlighting some of the features that you should consider and not actually designing them, is because the designing portion has been covered in previous webinars. But if you would like to see a little bit more, we can send those links out after this webinar as well. So that once we've finished designing our base structure, really it's just to make sure it's as rigid as possible. We'd like to attach our structure or our gantry robot to it. With this in mind, Vention has designed specific tools to actually, or this specific mounting plates to attach these structures together. These can be found in the enclosed timing belt actuator section, and they are called the self-aligning mounts. So what I'll be doing is dropping 2 of them into the design over here since we have 2 different versions. So essentially, the purpose of the self-aligning mounts is it allows you to install 2 parallel actuators without the need for high precision tooling. So say you do attach to actuators and say it can be up to 5 millimeters misaligned and still have your Z-axis or your other axes travel in their intended direction without any unwanted motion left or right. So the way they work is you both have a leader that has the ability to rotate around the X, Y, and Z axis, and a follower that can rotate around the X, Y, Z with an additional translational degree of freedom. So this, as it travels along, if you do have your system slightly misaligned, it will accommodate for that misalignment. So the way that I would recommend, the way that it should be used is you have all the leaders along one side and the followers along the other. The way they should be mounted is that you should have a spacing of no more than 1 meter between each plate. So in this case, if we have a actuator of 2,295 millimeters in length, we'll have 1 plate at either end and 1 in the middle as well to properly support the load. With that, it will be fully supported. And once actually attached to your structure, the system is fully constrained. You are not able to say wobble or move it if you do push it with your hand. It's really only during operation that they do accommodate for those slight misalignments. So with this, I'm gonna actually jump to our finalized design that does have all of these small additions that should be really taken into account when doing the final or essentially the last mile of your design. So again, I'll close this one off over here and open up our finished design. So some of the things to consider as this loads up. I do know we are at approximately 23 minutes, and I'd like to leave a little bit of time for participants to ask questions. Things to consider when doing the design like this are to reposition your sensor mounts. So all of our enclosed actuators do have built-in sensor ports that can be used if, say, you're doing a single linear axis. However, if you are using them for designing a gantry robot, when you have a frame, it does actually limit the overall travel of your actuators, and this does have to be taken into account, or you will have a collision of your Z-axis, X, or Y into the edge of your system. So if I go into the design over here, I can actually highlight what I'm talking about. So these are the sensor ports that you'll notice over here, but we have repositioned the sensor location by adding an extrusion profile, as well as our universal sensor bracket. The reason being, if I do a top view, if the actuator does travel all the way to the far right side, the Z-axis will impact the edge. With this, it does prevent the impact from happening. And we have replicated this on the X-axis as well. So the Z-axis sensor is nothing hindering its motion. Those you can use the standard sensor ports. The other 2 things that I would like to highlight are the drag chains over here. So Vention is able to supply cable management systems, and it is highly recommended if you do have cables that travel along with the gantry plate. This really prevents them from tangling up and keeps your machine looking clean. One of the final things that really should be considered when designing gantry robot is safety. So for safety systems, Vention is also able to supply these as well. So both you have e-stops on the pendants themselves, e-stop and reset modules that can be located at any point along the structure. Say you are opting for a door type enclosure, we do have gate bolts with safety interlocks. If you're looking for a little bit more ease of access, we also supply light curtains and laser area scanners. And finally, just to prevent areas or prevent operators from accessing areas that they really should not, we do have paneling. So all our panels can actually be automatically generated directly in Machine Builder. And if you're curious about seeing this, we both have a tutorial, and it is covered in both the first and second webinar that are posted on our website.